Hello, everyone. Thanks for watching this video. My name is Mahyar Fazliab. I am an assistant professor in the Department of Electrical and Computer Engineering at Johns Hopkins University. This tutorial talk provides an introduction to neural network analysis via semi-definite programming. Over the past decade, there has been a surge of interest in using deep learning technologies in a variety of domains, especially autonomous systems, where in these systems, neural networks have been successfully developed and deployed in various parts of the control pipeline, such as perception module, planning module, or even low-level feedback controllers. And actually, neural networks have been very successful in achieving superior performance and accomplishing complex control tasks. However, despite this great success, there are certain limitations that hinders the adoption of deep learning technologies in physical autonomous systems. And one of these main limitations is the issue of brittleness. It is now relatively well known that neural networks can be quite fragile to adversarial attacks and input perturbations. And in order to adopt deep learning technologies in safety critical systems, such as autonomous systems, we need strict guarantees of stability, performance, robustness, and safety. So in this tutorial, I'm going to primarily focus on this block diagram where we see a neural network driven dynamical system. So we have an uncertain dynamical system in feedback interconnection with a neural network and subject to external disturbances. So the main goal here is to verify a property about this closed loop system for all possible realizations of modeling uncertainties and external disturbances. And this property could be either stability, robustness, or safety. For instance, in safety verification, our goal is to verify whether a given set of initial conditions are not driven to an unsafe region in the state space. So in order to verify the safety, we need to actually compute the reachable sets for a finite time horizon. However, this is typically computation intractable, especially when we have neural networks in the closed loop system. So we need to resort to over approximating the reachable sets. So this tutorial is about introducing a recent framework that I have been developing along with my colleagues, which is based on semi-definite programming to provide guarantees of stability and safety and robustness for neural network driven system. And our approach for developing this framework is to abstract various nonlinearities in this closed loop system, or more in particular, the neural network by quadratic constraints. And we are going to argue that we can analyze the abstracted system using semi-definite programming. So the materials in this tutorial are primarily based on the following 5 publications, and the code for all the tools are available in the following GitHub repo. So I'm going to first start with analysis of neural networks in isolation, and then I will go back to neural network driven dynamical systems. So in neural network reachability analysis and verification, our goal is to compute or at least localize the output reachable set of a neural network given a set of inputs. So this problem arises in several contexts. For instance, in robustness certifications of neural networks, here we have an example about neural network classifiers. Suppose that we train a neural network to classify a given data set. For instance, here, the data set are handwritten digits. After training the neural network, one way to measure the robustness of the trained neural network is to consider a sample image and consider a set of perturbed versions of that image, such that all these perturbations are visually the same digit. And so in order to measure the robustness of the neural network, our goal is to verify whether all these perturbed images are classified correctly. So this is an instance of reachability analysis for neural networks. More generally, we are interested in analyzing the worst case behavior of a neural network for a given set of inputs. So we define a performance function J on the output space of the neural network, and our goal is to find the worst case value of this performance function, or at least find an upper bound on the maximum value of this performance function when the input of the neural network belongs to some bounded set. So this is obviously a non-convex optimization problem because of presence of nonlinearities in the neural network. So a lot of methods have been developed to solve this problem, either globally for the worst case value of the performance function, or at least find upper bounds. So in particular, satisfiability modulo theory and MILP solvers solve this non-convex optimization problem for the global solution. However, these methods are not scalable with respect to the size of the neural network or with respect to the size of the input set. So we have relaxations of this non-convex optimization problem where various classes of convex relaxations have been developed, in particular linear programming, which is the most scalable or at least accurate convex relaxations of this non-convex problem. And we have semi-definite programming, which is relatively the most accurate but least scalable. So in all these convex relaxations, are guaranteed to provide upper bounds on the worst case value of the performance function. So before describing our framework, which falls into the second category, in other words, the convex relaxation, or more specifically, a semi-definite programming approach. So let me briefly discuss the architecture that we are considering. So we are considering feed-forward, fully connected neural networks where we have cascade connection of L layers. Each layer consists of two operations. The first operation is an affine operation defined by the weight matrix WK in layer K and bias vector BK, followed by a nonlinear transformation defined by an activation layer, which is basically a concatenation of activation functions. So given this architecture, so our framework starts by having this simple but powerful observation that the neural network can be interpreted as a linear time varying system with nonlinear feedback. So here, the linear time varying part are actually the affine transformations in the neural network, and the nonlinear feedback is actually the activation layers of the neural network. So I'm assuming here that all the activation layers are the same. And for a neural network with L layers, so this dynamical system interpretation has the L time indices. So for each layer, we associate a time index, and the input to the neural network corresponds to the initial condition for this dynamical system. After this interpretation, we are going to use a quadratic constraint to abstract away the troublesome component of this dynamical system, which is the nonlinearity. After this abstraction, the simplified system is going to be just a linear system subject to quadratic constraints. And then we are going to argue that we can analyze this abstracted system using semi-definite programming because everything is either linear or quadratic. And also it is important to note that any property that we can prove for this abstracted system will automatically hold for the original system as well. So let me start by explaining how we actually do this quadratic constraint abstraction for the neural network. So start by single activation functions. So for a nonlinear function phi, we are going to describe this function by quadratic constraints that this function imposes on its inputs and outputs. For example, let's consider the class of sector-bounded nonlinearities, meaning that suppose that our function phi lies in a sector formed by lines with the slope alpha and beta here. So for this activation function, this quadratic inequality holds for all possible input-output values. However, this function phi is not the only functions for which this quadratic constraint is satisfied. Actually, any function in the shaded region in this sector satisfies this QC. So basically what the QC description of the activation function here is doing is it is over approximating the graph of this function, which is a set in 2 dimensions, by this shaded area, right? So given this interpretation, we can actually abstract or over approximate sets in general. And for the particular case of nonlinearities, this set is induced by the graph of the nonlinearity. So let's consider a simple example for the ReLU function. So suppose that we have the ReLU function over a finite interval. So we can basically describe this ReLU function precisely by intersecting 3 sectors. So the first sector is actually the boundary of a sector. So the corresponding quadratic constraints is of equality form. And the other 2 are the whole sectors with inequality form, and the centers of these sectors are shifted away from the origin. So it's not hard to verify that by intersecting these shaded areas in pink, we can recover the ReLU function exactly. So having described the ReLU with these three quadratic constraints, we can actually combine these quadratic constraints. We can add them together by multiplying them by arbitrary multipliers, lambda1 and lambda2 and nu, and then we obtain a single quadratic constraint that holds for all input-output pairs of the ReLU function for any arbitrary choice of the multipliers. So lambda1 and lambda2 are for inequalities. We require them to be non-negative. For nu is for the equality constraint, and there is no restriction on the sign of nu. So what we are doing actually here by adding a linear combination of these QCs is to actually we are deriving a parameterized over approximation of the graph of the ReLU, right? So and this over approximation it depends on what value we choose for this multiplier. So here you can see some sample realizations of the over approximation for different choices of multipliers. Regardless of the choice, the over approximation is always guaranteed to be an over approximation. So in the final STP that we develop for neural network reachability, so depending on what objective we are optimizing in that semi-definite program, then a proper values for these multipliers will be chosen by the STP. So these multipliers will be the decision variables in the final optimization problem. So after abstracting a single activation function by quadratic constraint, we can repeat this process, abstract all individual activation functions in a single activation layer, and then by simple linear algebra manipulations, we can basically translate these QCs into QCs for a whole layer consisting of an affine transformation plus an activation layer. And for layer K, we denote by lambda K and nu K the vector of multipliers for that layer. So here we have we are basically finding a parameterized over approximation of the graph of layer K. So let's put the pieces together here. So we have a neural network with L layers and input set to the neural network. And we would like to say something about the output reachable set. So first we abstract all the layers with their corresponding quadratic constraints parameterized by multipliers, and then we also abstract or over approximate the input set by its quadratic constraint. So given that all these QCs hold simultaneously, the main question we ask here, when is it true that a quadratic constraint holds on the input-output of the neural network? To answer this question, as basically all we need to do is to use the S procedure. So S procedure is a procedure to conclude the satisfaction of a quadratic inequality based on satisfaction of some other quadratic inequalities. And this procedure allows us to find a sufficient condition in terms of a linear matrix inequality to verify an end-to-end quadratic constraint for the whole neural network. And this LMI is basically our semi-definite program. So here's the main result after this procedure. So we obtain a linear matrix inequality of the form M of lambda nu and S less than or equal to 0. Lambda and nu are the vectors of multipliers for the all layers together and the input set, and S is a given symmetric matrix. So if this linear matrix inequality is feasible, so for some values of the multipliers, then then this is sufficient to have a quadratic constraint on the map of the neural network defined by this symmetric matrix S. So basically, we have this LMI, so it's worth noting that the size of this LMI is nx plus n times nx plus n, where nx is the input dimension to the neural network and n is the number of neurons. And the number of decision variables or the number of multipliers scales linearly with the input dimension and number of neurons. So let's see how this this LMI result is useful for verification and reachability analysis. Let's suppose that we would like to certify affine constraints on the output of a neural network. So this means that for a given input set to the neural network, we would like to verify whether the output of the neural network doesn't intersect a given hyperplane. And this hyperplane is defined by normal direction C and offset B. So if we define the matrix S in the previous slide like this, then the satisfaction of LMI provides a sufficient condition for the output reachable set to not intersect this hyperplane. So this is a verification algorithm. So in order to find the closest, actually we can go beyond verification and do reachability analysis, or we can basically find the closest hyperplane to the output reachable set by just minimizing B. And we note that the linear matrix inequality is actually linear in B. So everything is linear in the constraint. So we have an LMI constraint, and the objective is the offset of the hyperplane. So this is a semi-definite program for finding the closest hyperplane. If we repeat this process for multiple hyperplanes, we can find the smallest over approximation of the output reachable set in the form of intersection of half spaces. So let's consider also certifying convex quadratic constraints. In other words, our goal is to verify whether the neural network output reachable set is contained in a given ellipsoid. So by defining the matrix S and parameterize it by matrix A and vector B in the following form, then the satisfaction of LMI means that the output of the neural network will be contained in the ellipsoid defined by A and B. So basically the matrix A defines the shape of this and orientation of the ellipsoid, and B kind of determines the center of this ellipsoid. So we can, similar to the previous slide, we can also find the smallest over approximation of the output reachable set by actually minimizing the volume of the ellipsoid, which corresponds to and is proportional to minus log determinant of matrix A, subject to the matrix inequality constraint. However, unlike the previous slide, the parameters of this optimization problem A and B they do not appear linearly or in a convex way in the constraints. However, we can convexify this LMI, this matrix inequality constraint using short complements. So to the best of our knowledge, this is the first convex optimization based framework to propagate ellipsoids through neural networks. So here's a simple example on randomly generated neural networks with 2 inputs and 2 outputs, so that we would be able to basically compute the output reachable set exactly and visualize it. So here, the blue point cloud is the exact output reachable set. The red polytope is the reachable set computed by the STP that I just described. We call it deep STP. And the other polytope in dashed black is actually another method to find to over approximate the output reachable set. But this method is also based on a semi-definite relaxation of the problem, but the way that the problem is relaxed is different from our approach, and it is based on the idea of lifting in a non-convex, quadratically constrained non-convex problem, a quadratic problem. So here we are illustrating this approximation for 3 different number of layers, for 1 layer, 2 layer, 3 layers, and we can see, especially for deep, relatively deep architectures, our method is able to reduce conservatism of the semi-definite relaxation considerably. So after analyzing neural networks and performing reachability analysis, we can basically consider reachability analysis of closed-loop systems, in particular an LTI system in feedback interconnection with a neural network. For simplicity, I'm not considering uncertainties here, but as long as these uncertainties can be captured and described by various forms of quadratic constraints or integral quadratic constraints, then we can also incorporate them into this semi-definite programming result. So for this particular case, basically we can, for instance, certify affine constraints using exactly the same semi-definite program that we just developed. We only need to change the matrix S and parameterize it in this way. So if we define the matrix S in this way, where A is the state transition matrix of the LTI system and B is the input matrix of that system, C is the normal direction of the hyperplane, and B is the offset of that hyperplane. So if the LMI is feasible, then the output reachable set of the dynamical system at time k plus 1 will not cross the hyperplane defined by normal direction C and offset B. So here we are doing basically verification from step K to step K plus 1. We are assuming that the reachable set has already been computed at time K, and we are going to verify the next reachable set. So similar to the previous slides, we can also do reachability analysis and find the closest hyperplane by actually minimizing the offset B to find the closest hyperplane, and we can continue this process and to find the reachable sets. So here you can see another example where the system, the LTI system, is a double integrator. The neural network has been trained in a supervised manner to mimic an MPC policy. Here again, the blue tube is the exact reachable set. The red tube is tube is deep STP, and the black tube is the competitive approach. And as you can see, so our method is tight enough, provides tight over approximations, relatively tight over approximations of the output reachable set, so that we can verify that, for example, the trajectories do not intersect this horizontal line in the x1, x2 plane. And actually the trajectories also are driven to the origin. So we have another example for a 60 quadrature. Again, the neural network has been trained to approximate an MPC policy, and we're computing the reachable sets using ellipsoids. So far, we have only considered quadratic constraints. However, we can also consider different forms of QCs. So for instance, we can consider incremental versions of quadratic constraints, where instead of having only one input and one output, we have two input-output pairs. And these two inputs can belong to different, potentially different sets. And our goal is to verify quadratic constraints of this form, which holds incrementally with respect to this input-output pair. So why is this even important? Because verifying incremental quadratic constraints of this form becomes relevant in Lyapunov or contraction-based stability analysis of neural network-driven system, where one of these points is a reference point. For instance, it is an equilibrium point of the closed-loop system, or it's a reference trajectory for contraction-based stability analysis. Or for even neural networks in isolation, these incremental quadratic constraint is basically can capture several interesting properties about the neural network. For example, Lipschitz continuity in L2 norm of neural network is a special case of incremental quadratic constraint. So basically, we're going to see that how we can estimate the Lipschitz constant of neural networks using semi-definite programming, and estimating this quantity is actually useful in a variety of contexts, for example, for robustness analysis of neural networks and fast reachability analysis. So we are going to start with abstracting a very single activation function using incremental quadratic constraint, and the idea is to describe this function incrementally with respect to these input-output pairs. Here we see a simple example where we assume that our activation function is a slope restricted in an interval of interest, meaning that if we consider two arbitrary points on the curve of the function inside this interval, and the line connecting these 2 points has a minimum slope alpha and maximum slope beta, right? So this is called a slope restricted nonlinearity, and we know from robust control that basically we can equivalently describe this slope restricted condition using a single incremental quadratic constraint. So the approach for abstracting away the whole neural network incremental quadratic constraint is similar as before. So we first abstract a single activation function. We then add all these incremental QCs with the corresponding Lagrangian multipliers to abstract away all the components of the neural network, and then verify an end-to-end incremental quadratic constraint for the whole neural network using semi-definite programming. So here is an illustration of the result for the specific case that if we want to estimate the Lipschitz constant of neural networks using semi-definite programming. So the result is stated for one layer for simplicity. So the result is as follows. So we have this LMI constraint that if this linear matrix inequality is feasible for some choice of the Lagrangian multipliers and for some non-negative row, then square root of rho is guaranteed to be an upper bound on the global Lipschitz constant of the neural network. So basically, we can also optimize this upper bound using a semi-definite program, minimize rho subject to the linear matrix inequality. So the second application for incremental quadratic constraint is stability analysis of an LTI system plus a neural network controller. So suppose that we are given this closed-loop system, the initial condition belongs to some set D. So in order to do stability analysis, we can, for example, consider quadratic Lyapunov functions parameterized by a positive definite matrix P. X star here is the equilibrium point. And so after, so basically from nonlinear systems analysis, we know that basically if there exists a positive definite matrix P and a row between 0 and 1 such that these quadratic inequality holds for all x's inside the set of initial conditions, then the Lyapunov function will be guaranteed to converge exponentially to 0 with decay rate rho. So basically, this quadratic inequality in the middle is precisely equivalent to this exponential stability condition of the Lyapunov function. So we can see this quadratic inequality is basically an incremental quadratic constraint on the map of the neural network. So basically, we can again apply this procedure and find an STP or a linear matrix inequality as a sufficient condition for this quadratic inequality to hold. So we have the result in the following form. So if a linear matrix inequality is feasible, then we can guarantee exponential stability. So then we can search for a matrix P using semi-definite programming. So here's the last example. So we tested this last result on double integrator example in feedback interconnection with an approximate MPC policy. And on the right-hand side, you can see that you can see the region of attraction that we computed after computing the Lyapunov function. So the region of attraction is basically these blue ellipsoids, and the other ellipsoids are actually the exact reachable sets that we exhaustively computed by grid search. And you can, and this is just illustrating that this blue ellipsoid is indeed a region of attraction for the closed loop system. So now I would like to conclude my talk here by some conclusions. So we in summary, provided a semi-definite programming framework for stability analysis, safety verification, robustness certification of neural network-driven systems. So there are certain challenges for future work. For example, the most important challenge here is the issue of scalability. So these semi-definite programs are relatively difficult to solve compared to other relaxations. So in order to reason about modern architectures used in deep reinforcement learning and in other applications, we need to have scalable methods to solve these semi-definite programs. Another issue or challenge is large uncertainties or large input sets. So these semi-definite relaxations, although they are relatively accurate, all these convex relaxations, including the semi-definite programs, become quite loose for a large uncertainty. So how to overcome this, and for example, how to use partitioning of the input set in order to find better bounds is another direction for future work. And also how actually we can do robust learning. So throughout this talk, I just talked about verification analysis after training. So how we can incorporate this set of constraints during the training phase, where the goal is to train provably robust neural networks with desired guarantees. Thank you for listening to this talk.